Hello, welcome back to AE 3530, System Dynamics and Vibrations. In this video, we're going to start Chapter 2, which is going to focus on single degree of freedom vibrations. Today, we're going to focus on primarily transient or transient vibrations, and then in the future, we'll be going through forced vibrations. So vibration refers to an oscillatory dynamic response of a mechanical system. So this is an oscillatory type of motion, and it really focuses on the solutions to the equations of motion. So when we were dealing with dynamics, primarily, we were dealing with finding equations of motion. And now when we deal with vibrations, which is a subset of dynamics, we're now going to be focused on how do we solve these equations. We're going to be focusing on linear vibrations in this class. And if you want to learn nonlinear vibrations, which is much more involved and much more interesting as a result, feel free to reach out to me and I'm happy to have a discussion about that. But we're going to start by focusing on single degree of freedom in Chapter 2. When we go to Chapter 3, we'll deal with multi-degree of freedom, which will include 2 or 3 or more. And then we'll be dealing with what's known as modal analysis. Today, we're going to start with looking at what is called the simple harmonic oscillator. And we're going to consider the following system shown here, where the equation of motion is given as, or is, x double dot plus k times x, and there's no external forcing, so this is equal to 0. You would be able to derive this using the Lagrange equation or Newton's second law. Generally, when we're dealing with vibration problems, we're either going to be looking at a system where the equation is given, you might be asked to derive it, we'll give you the equation, or it's just a system where you can look at it and figure out what the equation is just by looking at it, at least with experience. We're going to start by dividing this equation by the mass, and this will result in x double dot plus what we'll write here is omega n squared x equal to 0, and omega n here squared is equal to k over m, and it has units of, and we'll use this equal sign with a dot, has units of radians per second squared, such that omega n equal to square root k over m has units of radians per second. So omega n is called the natural frequency of the oscillator, and it is real and positive. So to be clear, omega n here, we're going to write is greater than or equal to 0. Whether we're assuming 0 is a positive number. Now, if omega n is equal to 0, this implies that the spring, there is no spring or the spring stiffness is 0, and in that case we won't have any oscillation. So really we're going to assume here that omega is greater than 0. When we deal with multi-degree of freedom systems, we'll see cases where a natural frequency can be equal to 0, but in single degree of freedom we're not going to cover that case. Okay, so I mentioned that we're interested in finding solutions to the equations of motion. And in order to solve equation 2 here, we're going to provide an Ansatz. An Ansatz is just a German word that means an educated guess, meaning that somebody somewhere made a guess and they checked to see if their guess worked, and it turns out their guess was right. And now as a result, we now have this Ansatz. Now, an Ansatz doesn't mean you always know the answer. It just means that you're going to make an educated guess. You have some kind of insight into the problem, or maybe some intuition, and you think the problem or the solution should be something like whatever you decide. And then you're going to make that guess, plug it into the equation of motion, and see if it satisfies the equation of motion. Or follow the math and see where it takes you. And that's what we're going to do here. So our Ansatz is going to be, we're going to say our Ansatz, that's our educated guess. We're going to guess here that x of t is equal to some quantity. We'll write here, let's just use capital A times e to the lambda t, and then we can go and take the first derivative and then the second derivative, and we'll find here x double dot will be equal to lambda squared a times e to the lambda t. We're going to then substitute this into our equation of motion, into equation 2, and we're going to find that we'll get lambda squared a e to the lambda t plus omega n squared times a e to the lambda t, all equal to 0. From here we can collect similar terms. We'll get lambda squared plus omega n squared times a e to the lambda t, all of that equal to 0. So from here we really have two options. The first option is that everything in the parentheses is 0, and then the second option is a is equal to 0. Of course, e to the lambda t cannot be equal to 0 for all time, no matter what, for any value of lambda, unless lambda is minus infinity, in which case it's not a number. It doesn't really have a value in that sense. So that expression can never be 0, so that really gives us two choices. We're going to just note here that if a equals 0 is a trivial solution, meaning it's an uninteresting solution, it tells us that there are no vibrations going on. There's no oscillation of the system. Its amplitude is 0. And that implies then that the only interesting solution is that the quantity inside the parentheses must be equal to 0. So lambda squared plus omega n squared, that must be equal to 0. We can go ahead and we can solve then for lambda. Lambda will be equal to plus or minus the square root of minus omega n squared. I'm going to rewrite my square root just to fit everything in there. And from here, first of all, we're going to get two solutions. Lambda 1, 2 will be equal to plus or minus j omega n. And here, I'm going to move this green text up here. Here, j, and in this class, we're going to use j to represent the imaginary constant, or the square root of minus 1. Okay, so we have a lambda 1 that corresponds to the positive, a lambda 2 that corresponds to the negative. And just so you are aware, this is going to give rise to two constants. So lambda 1 is going to correspond to constant a1. Lambda 2 is going to correspond to some constant a2. And then our general solution is going to be x of t is equal to a1 e to the j omega n t, that's our positive term, plus a2 e to the j minus j, let me rewrite that, it should be e to the minus j omega n t, and that is our general solution. Oh, we'll try to draw a better square. Okay, so how do we determine these constants in equation 7? I want you to just take a moment, pause the video after I finish speaking, take a moment, think about how do we determine the constants. Okay, welcome back. So we can only determine the constants in equation 7 if we provide two conditions. That means that we need to specify what x of t is at two values of t, or we need to provide some conditions on the velocity or the acceleration or the jerk, which would be the derivative of the acceleration, or whatever you want to consider. You need to provide some conditions in order for us to be able to find those constants. Generally, we provide what are known as initial conditions, and this is what the starting conditions are of the system at time t equals 0, but it could also be time t equals whatever you want, t equals 5. If you choose some values at time t equals 5, you have two options. You can shift time and make t equals 5 your new 0, or you could also go backwards. You can run the equations backwards and ask what happened in the beginning in order to reach those values. What were the conditions at time 0 in order to reach what happened at time t equals 5 or whatever. But generally, we're going to look at initial conditions. We're going to assume that we start at time 0, and we'll shift time as necessary to start at time 0. And then we're going to choose an initial displacement. We'll use x0, and then we're going to use initial velocity, and we'll use v0 for this here. If we go ahead and we plug those into the equation, we will find that, and we do some algebra here, of course, we're going to find that a1 is equal to 1/2 times the quantity x0 minus j v0 over omega n, and a2 is equal to 1/2, it'll be the complex conjugate of that, 1/2 x0 plus j v0 over omega n. And now those are our constants, and if we go in and we plug those in, and then we apply some identities from Euler, we're going to end up being able to transform from exponential form into trigonometric form, and we'll get here that x of t is equal to x0 cosine omega nt plus v0 divided by omega n times the sine of omega nt, and that is the equation, or that is the solution for x of t given our initial conditions. Okay, so here we have both a sine and a cosine term. We are able to express these as a single cosine term with a phase shift, and we'll talk about that in a moment. In doing so, we're going to find here that x of t can be written as equal to, let's just say, some constant. We'll use big X here. Actually, we'll skip using X. We're going to use X later for steady state. Let's just use B here. Big B is equal to the, or big B times the cosine of omega nt minus a phase angle phi, where B here is equal to the square root of x0, we don't need those parentheses actually, x0 squared plus the quantity v0 over omega n, this quantity squared. And phi here is equal to the inverse tangent of v0 divided by x0 times omega n. And so we can express our solution in terms of sine and cosine, or we can combine it into a single cosine function. You can also do something similar if you want to use sine as well. In that case, you'll get a different expression for the phase angle, but it will ultimately be equivalent to what we just written down in equation 10. And so you can use either of these forms. It kind of depends on your initial conditions. For example, if one of your initial conditions is 0, it's much more convenient to use equation 9. Whereas if both of them are non-zero, it can be more efficient and easier to use equation 10. Okay, so the period of oscillation, or what we'll call big T here, this is equal to 2 pi over omega n, and the period of oscillation is the amount of time it takes for the oscillation to complete a single cycle, and we'll talk about that in a moment when we see the example response in the plot below. And so we mentioned that omega n is our natural frequency. That is in radians per second. If we want to express it in hertz, we'll use f sub n will be equal to first 1 over our period of oscillation, or expressed in the natural frequency, omega n divided by 2 pi. And again, this has units of hertz. So in the US, when we discuss natural frequencies, we often will use hertz, and I personally find this to be a more intuitive interpretation of natural frequency because it tells me how many cycles per second I should expect. But in Europe, often these are reported in radians per second, but they're equivalent, and it's important to be able to use both and understand the difference between them. All right, so in the plot shown below, I have provided just a plot of this example solution. You can see that at time t equals 0, we have some initial displacement x0, and then we have some slope here, and that is equal to our initial velocity. And we've delineated the point where we have a peak amplitude I'm going to draw on that with a blue dot. That's our peak amplitude. The period is the amount of time it takes to go from the one peak to another peak, or the repetition of that same peak. And the period is constant throughout all of the oscillations. You can pick any point on the curve, and it will the next time that point occurs will be a time big T away. This phase shift, normalized by the natural frequency, can be seen as the distance between the peak and the initial displacement shown here. And this amplitude C, in this graph, this is C. I used B here. So let's just equivalate these. So big B here is equal to this amplitude C, and that's just the amplitude of this overall response. Okay, we're now going to go through the first example problem shown here. So we're given that the block has a downward speed of 2 meters per second as it passes through its equilibrium position. So that tells us that x of t is measured from equilibrium, whatever that is. And we can say that the displacement x of t is 0 at that position. So it has a speed of 2 meters per second. The maximum, we're asked to find the maximum acceleration of the block over one cycle of oscillation. And we're given that the stiffness is 1,000 newtons per meter and the mass of the block is 50 kilograms. We're ignoring damping here, or any kind of damping, any kind of friction, and we're also neglecting gravity in this case. We don't really care about what caused the block to move with this speed. We don't care about what happened in the past to cause this motion. And that being said, we're going to assume that when it passes to the equilibrium point at 2 meters per second, we're going to assume or we're actually going to, it's not an assumption, we're going to set this, we're going to choose for that to be our time t equals 0. And as a result, we're going to form new initial conditions. So we can say here, using the information given, we form new initial conditions. We form new, we're just going to use ICs. We're going to abbreviate initial conditions for with ICs. And we're going to say here that x of 0 is equal to 0. That's in equilibrium. And x dot of 0 is equal to 2 meters per second. This tells us what our x0 is. This tells us what our v0 is. And given that x0 is equal to 0 here, it's more convenient for us to use equation 9 rather than using, equation 10. And we can see here that with x0 being 0, we won't keep the cosine term. We'll only keep the v0 over omega n times sine of omega t. So then we can write here, let's just say then, from equation 9, x of t will be equal to v0 over omega n sine of omega n t equal to 2 over omega n sine omega n t. So now we know what the displacement is. We need to do a couple of things. We need to compute the acceleration, and then we also need to find the natural frequency. Let's start with the natural frequency. Or in fact, actually, let's go and compute the acceleration symbolically, and then we will deal with the natural frequency, and then we will deal with how do we find the maximum acceleration. So let's just say that then the acceleration is, and we'll start by computing the velocity. X dot of t will be equal to, I said we'll do this symbolically, so we're going to have the derivative sine of omega t. We'll pull that on omega, lose the omega, we'll get v0 times the cosine of omega n t. This should make sense. If we plug in 0 for t, we will get back v0 times the cosine of 0 is 1 equals v0. So this makes sense. So then from here, x double dot of t is going to be equal to minus v0 omega n times the sine of omega n t. And one thing to note is that x double dot will generally be equal to minus omega squared times the displacement. This will generally be true, and then that should be omega n. For these problems, for undamped, unforced single degree of freedom problems, this will be true. There may be other cases where it's true, but we don't want to generalize. All right, so we now know our acceleration. We still need to find the natural frequency. So let's do that. We'll just say we need to find omega n, and as we saw previously, omega n is, well, we know what omega n, but let's just write out an equation of motion, mx double dot plus kx equals 0. We need our equation of motion for that. In fact, let's look at our problem here, our system here. That's what it should be, but if we look at our system, we see that there are actually two springs acting on the system, and as a result, the equation of motion is actually mx double dot plus 2kx is equal to 0. So therefore, omega n is going to be equal to the square root of 2k over m. And so it's whatever is in front of the x term, whatever is in front of that x term, that goes into our natural frequency. It is not just a single spring or k, it is everything in front of that x term, and everything in front of the mass or the acceleration term, that's what goes in the denominator. All right, so this is going to be equal to the square root of 2,000 divided by 50, and that's going to be equal to 6.325 radians per second. And as a result, we then can write out that x of t is equal to 0.316 times the sine of 6.325 t, and x double dot of t is equal to minus 12.649 times the sine of 6.325 t. Okay. We now need to consider how can we find the maximum acceleration. There are two options, or actually there are three options. So let's first just write to find the maximum acceleration. We have three options. First, we can compute the derivative of the acceleration, x triple dot, and then we can set that to 0, solve for t, and then plug in. So first we can compute x triple dot of t, set it to 0, solve for t, then plug in. Second, we can find the time when x dot of t is equal to 0, and we can plug that value of time in. That's because when the velocity is 0, both the displacement and the acceleration will be maximized. The third option is that we can recognize that the sine function in the acceleration has values somewhere between -1 and 1, and has a maximum value of 1. So we can recognize that the sine of 6.325, we'll just say Tm, that's the time of maximum, resides within, in fact, we'll just leave this as T for now. This resides in the domain of -1 to 1, such that the sine of 6.325 t, this must be equal to, well, it's either going to be -1 or it's going to be 1. And so we're looking for a maximum here. We'll just say this must be equal to 1. And therefore, we can actually go and solve for the t, and that should be t sub m. Let me correct that. It should be t sub m. That's the time of maximum. Should be equal to 1. When that is equal to 1, we can clearly see that the maximum acceleration is going to be minus 12.649, or this could be equal to -1. And then what we'll see from there, if we go with number 3, from 3, we find that maximum value, we'll just say max x double dot, must be equal to minus 12.649 times the sine of 6.325 Tm is equal to minus 12.649 times -1 equal to 12.649 meters per second squared, such that the maximum, we'll write this out, the maximum acceleration is 12.649 meters per second squared. And that is the answer to the question posed.